Hi BC Cal students, this video is over Taylor polynomials. So let's talk about what a Taylor polynomial is. A Taylor polynomial is an infinite series that is meant to represent an often complicated function. Now we're going to use elementary functions that we have already explored, e to the x, sine, cosine, to illustrate this example. But they can be used to calculate complicated derivatives or complicated integrals because polynomials are easy to integrate or derive. Some of you will go on to engineering and you'll see that you can use Taylor polynomials to do like numerical methods and things that calculate all kinds of things that I have no idea about. Like fluid dynamics, thermodynamics, and stuff like that. You can use Taylor polynomials to illustrate that concept. One of the things that we're going to see is this is the graph of what we're going to do in example 1. What we have here is a 6th degree Taylor polynomial. And for example 1, that Taylor polynomial is centered at x equals pi, which is about right here. So you can see that the blue graph is a Taylor approximation, and the red graph is the graph of cosine. So a Taylor polynomial is just an approximation at a localized value. And the more terms that Taylor polynomial has, the more accurate that Taylor polynomial is. So the key Taylor polynomials that we generally examine are the first derivative, which we already have done when we did linearization, and a 2nd degree Taylor polynomial, because that allows us to look at concavity, find relative maximums and minimums using the 2nd derivative test for extrema. So beyond that is just to add more precision, but the 1st degree and 2nd degree Taylor polynomials are incredibly useful because they allow you to analyze a function that may not be able to be analyzed easily under other circumstances. So the formula that we have is Pn of x is f of c plus f prime of c times x minus c plus the 2nd derivative evaluated at c times x minus c squared over 2 factorial. And again, the first part of this is just linearization. We've already done that when we did linearization and differentials. This was the formula for linearization. Remember, we wrote P1 of x was equal to this. And then if we extend out to include 2 terms, this is a 2nd degree. Can I spell degree right? Okay, D-E-G-R-E-E. It's been a long break. So here, this allows you to find things like, the 2nd derivative allows us to find concavity, points of inflection. We can use it to find relative extrema. Even if we don't know the function, we just have an approximation for it if we can find a critical value. So then after we add the 3rd degree onwards, it's just to provide extra precision. So again, C is the center of the series. The more terms we have, the more accurate. We're going to do example 1. We're going to find the 2nd and 4th. Let's not do the 6th. It's just overkill. So if we're going to do the 2nd and 4th degree, let's just go out to the 4th, which means that we need the 4th derivative. So we have f prime of x f of x is cosine x. So f prime of x is negative sine x. F double prime of x is negative cosine x, the 3rd derivative. And when we get to the 3rd derivative onward, we just use a number instead of Roman numerals. So f triple prime is sine x, and the 4th derivative is cosine x. So again, let's examine our formula. So these f of c values mean that you plug the center of your Taylor polynomial into each one of these derivatives. So that means that f prime of pi is going to be 0. F double prime of pi is going to be 1. The 3rd derivative at pi is going to be 0. And the 4th derivative at pi is going to equal -1. Oh, we also do need f of pi by itself. So f of pi is just -1. So when we write our fourth degree Taylor expansion, we're going to have P4 of x is f of pi. So we'll just write out how we would if we were doing a formula. So we're going to have f of pi plus f prime of pi times x minus pi to the first power plus f double prime of pi times x minus pi squared all over 2 factorial. I'm running out of room, so we're just going to put plus f triple prime of pi times x minus pi cubed all over 3 factorial. And the last term for fourth degree is going to be f 4 of pi times x minus pi to the fourth over 4 factorial. So when it says write a fourth degree, it means stop when you get an exponent of 4. And we'll see later on when we do power series that doesn't always mean that you have a common mistake is to think that you have 4 terms or you have to have 4 things that have a power. It means stop when you get to the exponent of 4 in a simplified version. So simplifying this, we get P4 of x is, so f of pi we know is -1. F prime of pi is 0. So 0 times x minus pi is just going to be 0. So we're going to have plus 0 plus f double prime of pi was 1. So we have 1 times x minus pi squared over 2 factorial, which is just 2. And then the third derivative at pi is 0. So 0 times x minus 3 cubed is 0 over 3 factorial, still going to be 0. So plus 0. And the last term is -1 times x minus pi to the fourth over 4 factorial, which is 24. So fully simplified, our fourth degree Taylor polynomial is -1 plus x minus pi squared over 2 plus, well, minus x minus pi to the fourth over 24. When we go into Desmos and look at that, we're just gonna, so what I have graphed right now is the sixth degree Taylor polynomial. We're going to take out the power of 6. So we're going to take that out and we're going to make this thing negative instead. So when we look at the graph, so we see that this fourth degree Taylor polynomial is, let's put in x equals pi as well. So we know at pi, we should get -1 as the coordinate. Close that down. So when x is pi, we see that, so this is the center of our polynomial, and we can calculate values exactly beyond just calculating x equals pi. We can suitably calculate 4. We can suitably calculate what happens when x is 2, even out to x equals 1.6. We see that there's almost no difference between the two function values, and we've zoomed in a ton. So even if we zoom in a lot, the difference is, so each block is 0.05. So that means this is 0.03 and that's 0.05-ish, or -0.03, -0.05. So these are very, very accurate polynomials close to the center. For example 2, we have a fourth degree Taylor polynomial, and we want to compare P of 1 to F of 1, and we should be centered at x equals 1/2. We're going to center that at x equals 1/2, not just do P4 of a half. So if we're centering this at a half, that means, and we're going to do fourth degree is going to be overkill again. It's too many terms. Let's go second degree to make this easy enough. So we're going to do second degree instead. So f of x is e to the 2x, and f of a half is equal to just e. f prime of x is 2e to the 2x, and f prime of a half is 2e. And then the second derivative is 4e to the 2x, so f2 of a half is 4e. So when we write our second degree Taylor polynomial, we're going to have p2 of x is equal to e plus 2e times x minus, again, x minus whatever your center value is. So x minus a half squared, nope, not squared, just to the first, and then plus 4e times x minus a half squared over 2 factorial, which is just 2. So if we're putting this into a calculator, I would recommend simplifying this and factoring out anything that they have in common. So that's going to make us take out an e. So we have 1 plus 2 times x minus, I'm going to write a half as 0.5. So 0.5 plus 2e times x, just 2, not 2e, plus 2 times x minus a half squared, because 4 divided by 2 is 2. So if we're comparing P2 of 1, that's going to equal, let's just throw it into the calculator. We have, so first we're going to do 1 stores as x, and then we're just going to type in our equation. So we're going to have e times 1 plus 2 times x minus a half plus 2 times x minus a half squared, and close parentheses, we press enter, we get 6.796. So 6.796 is what we expect for the approximation. And then if we just substitute in 1 to get f of 1, we see that f of 1 is equal to, so f of 1 is going to be e squared, and we can just throw that directly into the calculator. So e squared is 7.389. So 7.389. So that's a pretty wide margin of error, actually. So 7.389 minus 6.796 is 0.593. So let's see what happens if we add a third degree on. So the third degree means that we need a third derivative. So we're going to have 8e to the 2x. And so then the third derivative at a half is going to be 8e. And so then if we add on one more term, so then we'd have plus, so we'll do this up here. So plus 8 times e, so 8e times x minus a half to the third power over 3 factorial. So 3 factorial is 6. So that's going to reduce to be 4/3. So over here we'll have plus 4/3 times x minus a half cubed. So in our calculator, let's go back and add in one more term. So we're going to delete that, and we'll delete that parenthesis. So plus 4/3, so alpha y equals, so 4/3 times x minus a half, and we're going to do cubed, and now we close that out. And so now we get 7.2488. So now if we do P3 of x, so P3 of x is 7.2488. So we can see that adding one more term increased our precision by a lot. It went up by about 0.5, which is very close to this value. So again, the more terms we have in our Taylor polynomial, the more accurate our approximation is. So for example 3, we're just given a bunch of values. This would be the same as having a table, but we're just given f of 1 is 3, f prime of 1 is -6, f double prime of 1 is 5, the third derivative at 1 is -1, and we want to write a third degree Taylor polynomial centered at x equals 1, and let's see what we get. So in this case, we don't have to approximate anything because we don't actually have the actual function to calculate anything. So we just have to go straight to P3 of x is equal to f of 1, which is 3, plus f prime of 1, which is -6, times x minus 1, plus the second derivative, which is 5 times x minus 1 squared over 2 factorial, minus, well, plus -1 or whatever, minus x minus 1 to the third over 3 factorial. So we can simplify this to be 3 minus 6 times x minus 1 plus 5 halves x minus 1 squared minus x minus 1 cubed over 6. That's it. So for these examples where you have just basically a table of data given to you, you only have to write the expansion. You can't do anything more than that. At the start of the video, we said that a Maclaurin polynomial is just a Taylor polynomial centered at x equals 0. So when we write a 5th degree Taylor polynomial for sine x, or 5th degree Maclaurin polynomial for sine x, we're going to just have our center at, again, this means centered at x equals 0. So we still need to get a 5th degree, we need to go out to our 5th derivative. So f prime of x for sine x is cosine x. F prime of 0 is 1. The second derivative for cosine, the second derivative is going to be negative sine x. F double prime of 0 is 0. The third derivative is negative cosine x. So the third derivative at 0 is negative pi. The fourth derivative is sine x, and the fourth derivative at 0 is equal to 0. And finally, the fifth derivative is going to be cosine x, and f5 of 0 is equal to 1. So when we write our 5th degree expansion, we only need the non-zero terms. So we're going to have P5 of x, that's going to equal 1 plus 0 plus, well, let's start over. So I guess this should be G instead of F's. I forgot. We'll just change that to an F. So F of 0 is obviously 0. So P5 of x is 0 plus 1 times x minus 0 plus 0 plus -1 times x minus 0 cubed over 3 factorial plus 0, and then plus 1 times x to the 5th over 5 factorial. So we simplify this down to something that looks smaller, and without the zeros, we're going to have x minus x cubed over 6 plus x to the 5th over 120. So when we graph the you know what, we don't need to graph it. We're going to compare the values at, actually we'll graph it so you can see why there's going to be a disparity in some values. So we're going to have y equals sine x, and the expansion, the 5th degree expansion was I already forgot. It's x minus x cubed over 3 plus x to the 5th divided by 120. And so when we center that, that should be over 6, not over 3. My apologies. And so now when we see that centered at 0, that's going to be exact for a pretty wide range of values. And what we are approximating is g of 1. Well, I guess f of 1 since I wrote f's all over here. So f of 1 is f of 1 is the sine of 1 in radians. So the sine of 1 is 0.8415. So 0.8415. And P5 of 1 is, let's find out. So we substitute in 1. We're just going to have 1 minus 1/6 plus 1 over 120 is 0.8417. So we see that for x equals 1, these are almost exact. They're out to the tens, hundreds, thousands, 10,000s place accurate. So that's very accurate, 4 decimal places. If we look at f of 3.5, we're going to get the sine of 3.5. So the sine of 3.5, again, in radians, is negative 0.3508. And then P5 of 3.5 is going to equal, so now that's going to take a little bit of work. So we're going to do 3.5 stores as x, and we're going to type in our equation. So we have x minus x cubed over 6 plus x to the 5th over 120, press enter, and we get 0.73099, we'll say. So there's a pretty big disparity in those two values. And if we look at the graph, now again, remember our polynomial is centered at x equals 0. So the reason for that disparity is we are pretty far from the center of our 3x equals 3.5. So we're pretty far from the center of our polynomial. So when x is 3.5, what we get is a pretty wide range between those two things because we are very far away from the center of our approximation. So the thing that you should notice is when your values are far away from the center, your approximation is probably going to be way off unless you have like a very well-defined smooth function that has nice properties. You're going to run into a lot of error once you get pretty far away from the center of the Taylor polynomial. So when we do power series, we'll talk about the radius of convergence and see what values can be well approximated using a Taylor polynomial, but that's for a different video. So for example 5, we're given a Taylor polynomial and we need to find f of 4, f prime of 4, f double prime of 4, and the third derivative of f4. And we need to determine if the function has a relative maximum or minimum or neither at x equals 4. So we already have the third degree expansion. So generally speaking, P3 of x is going to be, well, centered at 4, is going to be f of 4 plus f prime of 4 times x minus 4 plus f double prime evaluated at 4 times x minus 4 squared over 2 factorial, which is 2, plus the third derivative at 4 times x minus 4 cubed, and all of that needs to be divided by 3 factorial, which is 6. So this is how every third degree Taylor polynomial evaluated at 4 would look. Specifically, we know that our P3 of x is 2 plus, we don't have an x minus 4 term to the first power, so we're going to put in a 0. And then the second degree we have, well, minus 5. So minus 5 times x minus 4 squared over nothing. So we'll just leave that there. So then plus 8 times x minus 4 cubed, and that's it. So if we're trying to find the f of 4, f prime of 4, f double prime of 4, and f3 of 4, we know that f of 4 directly equals 2. So f of 4 has to equal 2. And since the x minus 4 term is missing down here, that's going to imply that f prime of 4 equals 0, because only 0 times that can make it disappear. And then the coefficient for the x minus 4 squared is -5. So that means that f double prime of 4 divided by 2 has to equal -5. That's a pretty straightforward equation. So f double prime of 4 divided by 2 equals -5. So the implication is that f double prime of 4 is -10. We can add that over here. F double prime of 4 is equal to -10. And in a similar way, the third derivative of 4 divided by 6 needs to equal 8. So f3 of 4 divided by 6 has to equal 8. Multiply both sides by 6. So the third derivative at 4 is equal to 48. So f3 of 4 is equal to 48. And so the second part of this is we need to determine if we have a relative maximum, a relative minimum, or neither at x equals 4. Now, the only way you can have a maximum or minimum at 4 is if f prime of 4 is equal to 0, which means that you have a critical value at 4. And so f prime of 4 is 0, so we do know we have a critical value. So we have a critical value here. And so remember, the second derivative test for extrema tells you that if the derivative equals 0 for a specific value, then you can use the second derivative to determine if the value is a maximum or a minimum. In this case, since f double prime of 4 equals -10, which is less than 0, we know that f of 4 is a relative maximum, because that's what the second derivative test for extrema tells us. If we had gotten a positive, this would be a relative minimum. And if we gotten 0, we would not be able to determine that, especially since we don't actually have the function. So finally, for example 6, it's an old AP exam question that I modified just a bit. The function f satisfies the equation f prime of x equals f of x minus x plus 3. We know f of 0 is 4, and we have to write a fourth degree Taylor polynomial centered at 0, which is just a Maclaurin expansion. So to write a fourth degree Taylor polynomial, we need 4 derivatives. We're going to have, well, we already know f of 0 equals 4. So then f prime of 0 is going to equal f of 0 minus 0 plus 3, which is 4 minus 0 plus 3, which equals 7. And then we're going to use f prime of x to find the third derivative and the fourth derivative. So we'll carve out some room over here. So f double prime of x is going to be f prime of x minus 1, and the derivative of 3 is 0. So then f double prime of 0 is going to equal f prime of 0 minus 1, which is 7 minus 1, which is 6. So f double prime of 0 is equal to 6. And then if we do the third derivative, we're going to have the derivative of this equation. So the derivative of f prime is f double prime of x, and then the -1 just goes to 0. So then the third derivative at x, f triple prime of 0 is equal to f double prime of 0, which equals 6. And so then even the fourth derivative, oh, I'm sorry, I'm off the page. So starting here, the third derivative is equal to the second derivative, and the fourth derivative is equal to the third derivative. So that's going to imply that f4 of 0 equals f3 of 0, which equals 6. So at this point, every derivative after the second derivative, from the second derivative onward, is going to be 6. So if we write our expansion, we know that P4 of x is 4 plus 7 times x minus anything. So 4 plus 7x plus 6x squared over 2 factorial plus 6x cubed over 3 factorial plus 6x to the 4th over 4 factorial. And for your final answer, because it's just a Taylor expansion, they don't actually want you to simplify it. You could just leave it like this. You could simplify if you wanted to. 6 divided by 2 is 3. 6 over 6 is 1. 6 over 24 is 1/4, but you do not have to. So that concludes this video over Taylor polynomials. If you guys have questions, feel free to contact me via email or at Moto. I do miss seeing you guys in class. I hope you all are doing very well.